Okay, so this is our investigating fuels practical. Now I'm just going to show you this for one fuel rather than the 3 different fuels. But we should be able to then, I can show you how to collect the data, how to set up the experiment, how to do the calculations. Okay, so what we're trying to do is we're trying to compare the energy that is being given off when we combust different fuels. And the easiest way to do that is to measure the energy that's been transferred to water. Okay, so what we have here in this tin, okay, is some water, a fixed volume of water. We're going to measure its temperature before and after the experiment, so we can measure how much it's increased by, and we can use that and a calculation in a minute to work out the energy that has been transferred to the water. We are also going to measure the mass of the fuel before and after, so we can work out how many grams of fuel were actually combusted, and then we should be able to work out how many joules of energy were transferred to the water for every gram of fuel. And then if you were to repeat that for different fuels, you'll be able to compare the joules per gram for each fuel and work out which fuel is giving the most energy per gram of fuel combusted. So to start with, we've got our metal tin. Now the reason we're not using a beaker here is because we want to maximise the energy transfer from our fuel to our water, so we use a good conducting material. Okay, the technical term for this is a calorimeter, but I'm sure you will see that this is just an old bean can. It does the exact same job. It's just a metal can, so we get a good transfer of energy from the fuel to our water. So I've measured out some water using a measuring cylinder because we want to make sure we've got a fixed volume in there. So we've got 200 centimeters cubed. And we're going to keep the volume of the water the same, that's very important. We're going to record the initial temperature, which is 24 degrees. So there's our initial temperature. And before we start, we also need to know the mass of the burner. So we're going to turn on our balance. Make sure it's tared to 0. And we're going to measure the mass of our burner and the ethanol in it. So the initial mass, 212.011 grams. So what we're now going to do, place it underneath there, get a lit splint and light our burner. And what we're going to do is we're going to heat it until the temperature has risen by 20 degrees. Okay, so we're just going to keep that underneath there and keep an eye on the thermometer until it's risen by 20 degrees. So it started at 24, so we're going to heat it until it reaches 44. Now, while we're waiting for that, we can talk about the variables in this experiment. So we're going to be comparing different fuels. Okay, so our independent variable is always what you're changing. Okay, and the thing that we are changing is the fuel. So we've got ethanol here, but when you turn the page, you'll see there's 2 different fuels you need to compare them to. So the fuel that's being used is your independent variable. Your dependent variable is what you are measuring, and we are measuring the temperature change. Okay, so the temperature change in this case is going to be our dependent variable. And then the control variables are all the things you need to keep the same. So when we repeat this, or if we were to repeat this, because I'm not going to do this for all 3 fuels, I'm just going to show you the one fuel. But if we were to repeat this, we would need to make sure that we use the same volume of water. So we use 200 centimeters cubed. For this experiment, we'd need to use 200 centimeters cubed for all the other fuels. The other things we need to keep the same. We need to make sure that this calorimeter or this can is the exact same distance from the fuel burner for all the different experiments. we would need to use fresh water each time so that it has a similar start temperature. It doesn't have to have the exact same start temperature, but it helps if it's similar. Okay, so we want to start at approximately 24 degrees. It doesn't matter if it's 23 or 22, as long as it's about the same. And again, we're just measuring the rise of 20 degrees. So we are already at 39, so we're nearly there. And once we've got that temperature change, we're going to be able to calculate the energy that's been transferred. Okay, so as I'm talking, that has now reached 44, so we're just going to place the lid on there to extinguish our burner. So we've achieved a temperature change. Now, it doesn't have to be exactly 20 degrees. It just needs to be approximately 20 degrees. So I'm just going to leave it for a second so that the thermometer can stop moving, because there's a little bit of temperature lag. You know, the thermometer doesn't give you the temperature in real time, so it might go a little bit higher than 44. So while we're waiting for that, I'm going to reweigh the burner, and again I'm going to make sure it's got the lid on it, the same as it was before. So now it has a mass of 210 grams 851. Now, you don't need to measure it to 3 significant figures, it's just that the balance that I've picked has an accuracy of 3 significant figures. So now we can calculate the mass of ethanol that has actually been used in the reaction by subtracting the final mass from the initial mass. So 212.011 minus 210.851. So that is a difference of 1.16 grams. So 1.16 grams of ethanol were used to increase the temperature by 10 degrees. And looking at the thermometer, that has stopped bang on 44, which gives us a temperature rise of 20 degrees, which is exactly what we were expecting. So you would then empty out this calorimeter, put fresh 200 centimeters cubed of water, make sure you put the can back in the exact same place so that it's the same height, and then you would be able to record the mass needed of different fuels to achieve the same temperature change. So if we turn the page here, we'll zoom in a little bit. Okay, this calculation here is going to allow us to work out how many joules of energy were transferred for each gram of the fuel used. So if we look at these values here, the 200, okay, that refers to the mass of water. Because for every centimetre cubed of water you have, it weighs 1 gram. We had 200 centimetres cubed, which means it had a mass of 200 grams. This 20 here, that was the temperature change. It increased by 20 degrees. So if yours increased by 21 degrees or yours increased by 19 degrees, then you would just change that number there. This number here is what we call the specific heat capacity of water. So what that tells you is that the energy needed to increase the mass of 1 gram of water to increase it by 1 degree centigrade is 4.2 joules for water. All substances have their own specific heat capacities, but we were heating water, so we need to use the specific heat capacity of water. So it requires 4.2 joules to increase 1 gram of water by 1 degree centigrade. So if we take the specific heat capacity times by the number of grams we had, times by the number of degrees it's increased by, we can work out the total amount of energy in joules that was transferred to our water. Okay, so 200 times 4.2 times 20. Okay, 16,800 joules was transferred to our water. Now we want to work that out per gram of fuel burnt. Okay, that's how much energy was transferred, but how many grams of fuel were needed to do that? So that's where we go back to our results. it took 1.16 grams. So we're going to divide that by 1.16. Giving us 14,482.8 joules per gram. Okay, and what we could do is if we worked out the joules per gram for propanol and butanol, we would be able to compare them, and then we could work out which one of those fuels was giving us the most energy in joules for every gram of that fuel burned. So it's not just about how much energy it gives you, it's about the efficiency of that energy. It's all well and good saying, oh yes, ethanol gives you more energy, but not if you have to burn more ethanol in order to get that energy. Okay, so by working out the energy to gram ratio, you can get a value that you can actually compare different fuels to identify which one is the most efficient fuel.